Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
Did you know that 1.3 billion years ago in a distant galaxy, two black holes were colliding, and they were spiraling violently into one another? This powerful merger sent ripples through the fabric of spacetime itself, and in the final tenth of a second, this energy that was released by the merger was 50 times greater than all of the energy emitted by the observable universe combined. Think about that for a second.
Ooh.
Yeah.
Yeah, this immense energy, which was traveling at the speed of light for a billion plus years, eventually reached our Earth, and then it subtly warped space, and this caused two light beams in a building with specially designed perpendicular pipes to come just so slightly out of sync.
Yep.
And this phenomenon allowed humans to detect gravitational waves for the first time.
And the challenge in detecting these waves is their minuscule effect. They alter space by just one part in 10 to the power of 21.
Oh.
Like, to put that into perspective, it's like measuring the distance of Alpha Centauri and detecting the changes in that as small as the width of a human hair.
Alpha Centauri, by the way, is the closest star system to our solar system. But it's like quite far as well, okay?
Very, very far.
Yeah.
So, to detect these tiny fluctuations, it's necessary to measure over a vast distance.
That's why the arms of something called interferometers, okay? Interferometers.
But the E is not there in it.
Arey yaar, grammar person. So their arms are like 4 kilometers long. And even with this length, gravitational waves only alter the arm's length by a maximum of 10 to the power minus 18 meters.
अरे बाप रे, इतना बड़ा?
Arey, slay point ka sarcastic humor. Just chill out.
Yeah. And by the way, that's the width of a proton divided by 10,000.
Oh.
The most precise measurement ever achieved.
So, how is it possible to measure like such a small amount considering all the other sources of vibrations and noise in our environment, like earthquakes, traffic, electrical storms?
Random people screaming.
Yeah, that's very normal.
Well, for one thing, the mirrors are the smoothest ones ever created. Like, that's a statement in itself. They weigh 40 kgs and are suspended by silica threads that are just twice the thickness of a human hair. And that's to isolate them from the environment. And even then, the only way to be certain, like to not be tricked by environmental noise, was to build two detectors far apart from each other. I think it's LIGO Hanford and LIGO Livingston.
Yeah, correct.
So the idea was to build two detectors far apart from each other in reasonably quiet locations, because you can't ever have anything
Correct.
perfectly quiet on Earth. And that allows us to distinguish between the local noise, which would only appear on one of the detectors, and gravitational waves, which should pass through both of them like almost simultaneously because of the literal scale of the waves and the distance between the observatories.
Yeah, and the next challenge is the laser.
Yeah, you need a laser that can provide exactly one wavelength.
Imagine trying to measure a distance with a ruler that constantly changes its length. Sounds crazy, right?
Yeah.
So if your laser wavelength is fluctuating and you're relying on light wave interference for measurements, the results would be completely unreliable.
True.
You wouldn't be able to determine the length accurately because your so-called measuring stick itself is continuously shifting.
Yeah, and a large portion of the equipment scientists use, around like 3/4 of it, is dedicated only to stabilizing the laser. By the end of this process, they achieve a stability of 1 part in 10 to the 20. To put that into perspective again, that's 1/100th billion of a trillion.
These numbers, God.
That's the level of precision they work with, bro. So the optimal lasers for this kind of measurement have a wavelength of 1064 nanometers or 1064 nanometers, which is in the infrared spectrum.
However, this raises another issue. How can you measure changes as small as 10 to the minus 18 with a wavelength of light that's only 10 to the power minus 6.
Yeah, 10 to the power 9 minus 6, as in 1064 nanometers. That's just to not let you all get confused. It's the same thing. 1000 nanometers is 10 to the
Yeah,
power minus 6.
sometimes these numbers can be a little confusing. That's why I'm a theorist. I don't work with numbers. I work with algebra. Okay. So as I was saying, it's easy to understand a large shift of like 90 degrees or 180 degrees in the wavelength.
Yeah.
Because we can see the dramatic changes easily. However, the reality is it's only 1 trillionth of a wavelength that the arms are shifting in length.
Yeah, it seems obvious that you can measure half a wavelength, right? Or
Yeah.
a full wavelength or whatever, because that will cause the light to interfere with itself and will go from like completely dark to completely bright. So we're actually looking at slightly darker or slightly like brighter. Is that what we're actually looking at?
Yeah, so the limit here at how good we can measure this difference between dark and bright has to do with the fact that light is what we call discrete. It
Yeah.
comes in discrete chunks or packets of light which are called photons. And I think it's light's dual nature which is famous enough for most of our listeners to know what photons are.
Yeah, wave particle duality is famous, all right.
Yeah.
But for those who may not be familiar, here's just a one-line explanation. Light is both a particle and a wave.
Mind blowing.
Yep. So the variation in the number of photons hitting the mirrors at any instant due this quantum uncertainty is proportional to the square root of the total number of protons. Okay? Simple as like the square root of the amplitude in like measuring the uncertainty,
Yeah, yeah.
the wave thing we did earlier.
Correct.
So what this means is the more photons you use, the smaller the uncertainty gets. That's a fraction of the total. This is why the laser power in the arms is exactly 1 megawatt, and that's like enough energy to power 1,000 homes, all in one light beam.
So even with a perfect laser and 1 megawatt of power,
Yeah.
anything the light hits would interfere with it, even the air. So all the air in the arms of the detectors have to be eliminated. And it takes around like 40 days to pump down just a trillionth of the atmospheric pressure inside the
It
tube.
takes 40 days to pump down to a trillionth, not a trillionth.
अरे हाँ रे वो ही ना मतलब
They're going to that, a trillionth atmospheric pressure. That low they're going to.
and the internal temperature of the tubes, it is heated up to the temperature of an oven to expel any other residual gases.
Fair
inside.
enough. And they've pumped out enough air in those 40 days to fill up 2.5 million footballs,
Oh.
making it the second largest vacuum in the world after the Large Hadron Collider, our favorite. Now, here's something most people don't think about, which is that gravitational waves stretch space-time, right? As we said earlier in the beginning of the show. So, light traveling through that space will also be stretched.
But if everything is stretching, how would you know that anything is stretching?
That's the conundrum, right? I can even say quantum conundrum because we'll just wait for that. It doesn't make any sense, right? Because the whole thing is bogus. Shut it down.
I agree.
Like, I would send a laser beam down this tube and wait for it to come back, but nothing would happen, according to me, because I wouldn't know if the space got stretched and the laser wavelength got stretched, right?
Yeah, well, you wouldn't come to know. So it looks like it looks the same whether you got it stretched or not stretched. I mean, that doesn't make a lot of practical sense, but that's the real world for you. So it's a matter of timing, and that's how it works. So the amount of time it takes for light to go down this tube and come back is extremely very short. You know the speed of light, right?
Yeah.
But however, the gravitational wave, when it comes through, it makes a very low, like humming sound, like
Do it again? Okay, I won't ask you to do it again. Fine. So it's this slow stretching. It's only 100 times per second. And it's true, when the wave comes through the light, which is in there, it actually does get stretched because of the feature of gravitational waves. And then that part doesn't do the measurement for us, but now the space is stretched. The laser has like come and gone. It's like out of the picture.
We're constantly basically shooting this laser back into the system. So the new fresh light goes through there and has to travel a bigger distance than the light before it.
Yeah.
And so by looking at how this interference changes with time and keeping the laser wavelength from the laser itself fixed, we're able to measure things.
So what was actually needed to detect gravitational waves was a megawatt of laser to minimize the short noise of exactly one wavelength, because we are trying to measure a trillionth of that wavelength, right, as we said earlier.
Yeah.
And that wavelength, that light has to be continually inserted to replace older light that's been already stretched and squished in the world's second largest vacuum chamber, second to only LHC. In like at a trillionth atmospheric pressure, hitting the smoothest mirrors ever created, suspended by silica threads that are, I think, two times the
Diameter of human
of
hair.
a human hair,
Correct.
at two distant sites to eliminate noise, with 4 kilometer long arms each to increase the magnitude of gravitational waves to just 1,000th the width of a proton.
Wow. Just wow. That was a mouthful.
Yeah, I forgot half of it also
Yeah.
while saying it.
So one of the things that was the most interesting to learn about this when we were like researching was what is limiting the sensitivity of the detectors today. And it turns out it is quantum mechanics, which is why Arna was saying something about quantum
Yeah.
conundrum, if you remember.
Yep.
And essentially you can think of it as its own Heisenberg's uncertainty principle in itself. We've got two things, and together their uncertainty has to be bigger than a certain value. Luckily for us, we are only like trying to measure one thing here, and we're not trying to measure two things at the same time.
And all we want to know is how much more one arm gets stressed from another arm to like show the difference. And that is the key point which people did not understand until recently. The way to build these systems is that they're extremely good in measuring one thing, in doing one specific task, and all the uncertainty which comes from quantum mechanics is completely crammed into another thing that we don't care about.
That's the absurdity of detecting gravitational waves for you.